Hello and welcome to another video. Today we're going to be talking about electric motors and the motor effect. So we've spoken about force before. Today we're going to introduce something called fields. A field is a physical quantity which we've spoken about before. This physical quantity has got a number at every point within the field. So throughout all space there will be a certain field, and at every point in that space in the field there is a number to represent that point part of space. The first thing to understand then for electric motors is that when we have a charged particle moving through a magnetic field, that charged particle will always feel a force. So if we have a charged particle, for example, an electron, and this electron is moving through a magnetic field, then this electron is going to feel a force. So now let's talk a little bit about electricity. So when we have a wire, the conventional current goes from positive to negative, but inside that wire, we actually have a flow of electrons. Because the electrons are negatively charged, the electrons move from negative to positive. So the opposite direction of conventional current flow. And this is just by definition. Electrons, as we've just spoken about, are charged particles. So in the wire, we have a flow of electrons and we have a current because of this. Because the electrons are charged particles that are moving in the wire, this means if we put the wire into a magnetic field, these electrons that are charged particles moving through a wire will feel a force because of what I've just spoken about. How if you have a charged particle moving through a magnetic field, it will feel a force. So, because the electrons in the wire are feeling a force, the overall wire is going to feel a force. And this is where electric motors come in. A little bit of preliminary knowledge that we need to know before we continue to discuss electric motors. And that's the left-hand rule, or Fleming's left-hand rule, as people know it by. So there's lots of different ways to remember this left-hand rule, but one that I found helpful when I was studying physics in school is the one that I'm about to explain now. So that would be, you put your hand out like this, and notice how every finger and the thumb that I am sticking out has got a 90-degree angle in between it. So this one is at 90 degrees to my thumb, this one is at 90 degrees to my middle finger, this one is also at 90 degrees to my thumb. So each thing is at 90 degrees, and that's important. So that's the first thing to know about the rule. So first of all, we have thumb. So in thumb, we have an M, and so the thumb is going to represent our motion. So the way that the thing we are measuring is going to move, the direction of the motion. And that's because thumb has got an M in it. So that's how we're going to remember this one. We're going to call this finger our first finger. And this, because it starts with an F, is going to be our field. So the direction of our field. And if you remember from previous videos, a magnetic field goes from north to south. So this one is for field, going from north to south. So north to south along the finger. This is our second finger, and because second has a C in it, this is going to be the direction of our current. And this is the direction of our conventional current, which means from positive to negative. So this is our current. So we have the direction of motion, thumb, first finger, field, north to south, and second finger, current. So there should be a diagram on the screen now, and this is of a simple electric motor. So the diagram that I have drawn is using a direct current, or a DC current. We can use Fleming's left-hand rule to explain why the wire will turn. We're going to explain this now. So if we just look at the left-hand side of the wire first, remember how I said that everything has to be 90 degrees to each other. So we're only going to be considering the left hand of the wire that's going sort of away from us, and the right hand side of the wire that's coming towards us. The parts of the wire, so the parts of the rectangle that are along the field line, so from north to south, we aren't going to be interested in, because if you remember, we want everything to be at 90 degrees to each other. Those parts of the wire are running parallel with the field. So there will be no force felt. So we're just going to disregard those parts, okay? The only place where the wire will feel a force is where the current is at 90 degrees to the field lines. So let's first of all look at the left-hand part of the wire. So on the left-hand part of the wire, we can see the current is running from positive to negative. So the current in this part of the wire is going to be going away from us. And we can also see on the diagram, the north is on the left and the south is on the right, and our field lines are going to be running from north to south. So that's from left to right. So we've got two bits of information there. Notice how we have 2 fingers and a thumb, so we need to know 3 things. But to figure out the final one, we only need to know 2 of those things. And we've got 2 pieces of information, so let's figure it out. So the first thing we picked up was the current. So remembering that second finger is current because of the C in second, we're going to place our finger from positive to negative. So that would be starting closest to us and pointing away from us, because that's the direction of our current. Then first finger field, well, that's going from north to south and that's going from left to right. So we need to turn our finger from left to right so that it's pointing to the right. And then we don't move our thumb at all. So we've set in stone where our current is flowing, where our field lines are flowing. So wherever our thumb is now is going to show us the direction of motion. So we can see the left-hand part of the wire is going to feel a force that is pushing downwards. Okay, that's great. So let's look at the right-hand part of the wire then. So for this one, we can see the current is coming from the back to the front. So let's set our current finger. So second finger current. So point that towards us, along the direction of the current. First finger field, that's from north to south. So that's left to right still. And don't move the thumb, remember, this just shows our direction of motion. So we can see that the right-hand part of the wire is going to feel a force upwards. So it's going to move upwards. So all in all, our left-hand part of the wire is going downwards, our right-hand part of the wire is going upwards, and so they're going to turn in an anti-clockwise direction. Okay, so we've discussed how the wire coil turns around. So let's just think about this. So initially we found out that our coil is going to turn in an anti-clockwise direction. Let's just look at the left-hand part of the wire then. So we found that our current is going away from us, our field is going from left to right, and we found the motion would be downwards. So as this left-hand part of the wire does a quarter of a full circle's rotation, our direction of field does not change, it's still going from left to right. Our direction of current does not change, direction of motion also stays down. So that's the left-hand part of the wire after a quarter turn. Let's look at the right-hand part of the wire after a quarter turn. So our current was coming towards us, our field was going from north to south, and our motion was going upwards. So after a quarter turn, the field doesn't change, the current doesn't change, and the motion doesn't change. So this is still going upwards. So the left-hand part of the wire is feeling a force downwards, the right-hand part of the wire is feeling a force upwards. These should be balanced forces, and that means the wire should not continue to spin. But the wire does continue to spin in an electric motor. So why might this be? Well, firstly, if you think about when you're pedaling a bike outside, when you're pedaling on the bike, if you all of a sudden stop pedaling on the bike, the wheels do not stop turning. As soon as you stop pedaling, you don't just freeze and the bike just stops turning. When you stop pedaling, the wheels on the bike continue for a little bit. That's because of the momentum. So it's kind of like what we have in our wire coil. The wire coil initially has some momentum because of the force that it feels. So it's not just going to all of a sudden lose this momentum because of momentum conservation. So therefore it will still keep turning. But mainly the wire coil continues to turn because of things called commutators. So on each side of our diagram, we have things called conducting brushes. And then we have the commutator that spins with the coil of wire. So when the conducting brushes and the commutator lose contact, as the wire starts to spin, the commutator loses contact with the conducting brushes. As the wire continues to spin 180 degrees on the other side, so half a circle's turn, it will reconnect with the conducting brushes. These conducting brushes are continuously supplying current in the same direction. Let's think about the current in the wire. So if we take the left-hand side of the wire first of all, initially the current is going away from us on our diagram. So if we lose contact at this conducting brush here with the commutator, when it does a half circle turn and rejoins here, the current reverses. So the current changes direction. Let's look at the right-hand side then. Initially, the current is in this direction. The commutator loses contact with the brushes, goes to the other side and reconnects with the brushes, so the current will reverse direction here and go that way. But if we look at our initial diagram, the current is initially going the same way. So if we use Fleming's left-hand rule again, we'll see because the current is going the same way still in the left-hand part, the force will be a constant force in the left-hand part felt downwards, and in the right-hand part constantly felt upwards, so we get this constant turning effect. So the commutator continuously reverses the direction of the current every half turn in order to allow us to have this constant circular motion in the electric motor. So why are electric motors important? Well, Michael Faraday found this brilliant thing that was later improved by James Henry to allow for this commutator and continuous circular motion of the electric motor. Well, electric motors turn electrical energy into mechanical energy, and this is used in everyday appliances around your house. It's used in things like hairdryers, washing machines, fans, electric drills, electric saws. So it's a really important piece of knowledge that physicists found that we can now use in everyday objects. Okay, let's quickly think about an equation. So we have the equation F, force, equals BIL. B is our magnetic field strength, I is our current in the wire, and L is the length of the wire. So if we want to increase this force, there are a few different ways that we can do this. So firstly, we can put a magnetic core into the centre. This soft iron core in the centre of the coil will concentrate the magnetic field lines. And this will overall increase our force and therefore increase the turning effect felt by the wire. Another way to increase the force and therefore the turning effect would be to increase the current in the wire. So if we increase something on the right hand side of the equation and keep the others constant, so in this case increase the current, then this will increase the thing on the side of the equation, in this case the force, and therefore the turning effect. And finally, if we increase the number of turns in the coil, this will also increase our turning effect.
Okay, to make sure you understand what we've just spoken about, have a go at this question. The wire will move, but in what direction will the wire move? You can see the current direction in the diagram. You know the direction that the magnetic field will go. Have a go at using the left-hand rule to deduce which way the wire will move. Okay, let's go through this question together. So we know that the magnetic field goes from north to south. So let's just draw that in. Using the left-hand rule, we can see our thumb will give us the direction of motion, our first finger will give us the direction of the field, which we know in this case. That goes from north to south, and in this diagram, north to south is from left to right, so let's put our finger in that direction. Our second finger is the direction of the current, and this is going from the top of the page to the bottom of the page. So north to south is our first finger, Direction of current is from top to bottom of the page in this diagram, and the motion we can see will therefore be given by the thumb, which is out of the page. So this wire will turn out of the page.
Thank you for watching till the end of the video. There will be a link down below which includes a feedback form. If you could fill this out, that would be excellent. Thank you for watching, and I'll see you in the next video.